So the best way to look at this presentation is if you got a technical hat, it is about testing new ideas, testing the daring ideas. And if you have a business hat on, it is about questioning yourself. Don't be disruptive, be the disruptor. So we are going to be looking at alternative engine technology, and we are going to be questioning ourselves how alternative engine technology can be fuel agnostic and yet provide high efficiency metrics. Within the scope of the hub, our work is pretty much firmly focused in the power and propulsion activities. So what we are going to do, a little bit about who we are. We are going to revisit some of the headline numbers. How are we approaching asking questions regarding disruptive technology? What sort of answers we are coming up? We are questioning conventional engines that are out there. What are we learning from our experimental activities? So everything that I'm going to be sharing is going to be embedded with experimental findings. 3 things regarding the experimental technology. We are going to come back to this word cool compression, internal heat recuperation, and optimization of combustion. And right at the end, I'll leave you with some take-home messages. If we recap 10, 15 years, what are the type of things that we have been actually up to? This is looking at the fundamentals inside an engine. So that's the optical engine, looking at diesel engine works, looking at large-scale waste heat recovery, hydrogen, methane engines, dual fuels, single fuels, and even looking at liquid air energy storage systems. So all of this thing has been happening at University of Brighton for the past 15 odd years. So everything backed by experimental results. Let's look at some of the headlines. So that's the map of the CO2 overall emissions. What are the pathways that are being considered to address? You can utilize LNG, you can utilize methanol, you still need carbon capture if you want to go carbon zero. Liquid hydrogen engines, pilot projects already out there. I found a phrase which is quite interesting. Somebody said to me that liquid hydrogen is the champagne of energy. It's for those special occasions. It is that energy intensive to actually make it right now. And also, there are activities that are happening on getting ammonia ships on the seas by 2026. We also need to learn from what is actually happening at the heavy-duty sector for road transportation, because their emission legislations are even more stringent. So there's a battery swap happening there on an all-electric vehicle in a China prototype project. The fumes coming out of this Mercedes truck is not exhaust gases. This is water vapor. This is running on fuel cell. There's a pure hydrogen truck that is running in US, and there's a company that have put their hat into making ammonia trucks also. There's a big debate. There's a lot of fuel options there. So you got different criteria here. You got different fuel metrics there. This is kind of a non-exhaustive list down there. But things that are being considered is the range of storage temperatures, how much energy you can get out of the fuel, how well the fuel burns in conventional setups, and how is it going to impact your overall shipping needs, how much cargo space reduction you're going to tolerate. If you now take a deep dive into the academic literature out there, you can pretty much break everything into step, stretch, and leap approach. Step, kind of lower hanging fruits, heat recovery systems. There are new heat recovery systems coming up. You can kind of tap into some of the waste heat recovery. Stretch end is looking at new engine cycles. And leap end, it's pretty much all the bells and whistles. So here you have a reformer, you have a fuel cell, you have an engine, everything working across different parameters. So what is the methodology that we use to ask ourselves, how do we consider disruptive technologies? So some of the questions like, why do we really want to do this specific task, and what physical principles are involved? These sort of questions may seem quite mundane, but we're trying to question ourselves, are we actually unknowingly coming up with a constrained solution or not? So we have 30 sets of questions we look at from 3 different perspectives. So from a business point of view, if you want to look at this, consider this as market and technology. So you want to do incremental innovation, disruptive and radical. Incremental, you got to ask the right question if you want the right answer. Disruptive innovation, what if I think exactly the way you think, and what if we both are actually wrong? But the fun bit actually happens in radical innovations when you say that what if a constrained variable that I have, a dependent variable that I have in my system suddenly becomes independent? That really opens new possibilities as far as new engine technologies are concerned. So we applied that methodology to systems approach, and we started looking at the overall engine architecture. What you're trying to do in a conventional four-stroke engine is you're compressing, you're doing your combustion, then you're doing your exhaust. So you want to keep it cool, you want to heat it up, you want to combust it, and everything is happening in that one cylinder. So we are really questioning ourselves, what opportunities can we actually gain if we were to separate these processes out and actually optimize each and every process? So thinking about radical engine technologies, but nonetheless engine technologies that pretty much utilize very similar engine architectures that we have right now. So this setup which we have in front of us, it's called a split cycle engine. It separates the compression and expansion and power generation into two separate parts. So you have more variables you can tune, you have more variables that you can actually optimize. So in effect, what happens is you have your intake air, you have a compression happening that delivers high compressed air, it goes through expansion, you have a combustion, exhaust. The key thing to keep in mind here is the compression, you're trying to keep it as cool as possible. You're trying to recover all the exhaust waste heat by that red heat exchanger in the middle. And you're also able to fully optimize what is happening at your expansion cylinder, which is your power generation end. Now, we undertook lots of experimental activities trying to optimize these subsystems and try to connect them, all of them up in an overall systems approach. So, at the compressor end, this is what our compressor test bed looked like. So this is our compressor setup. This is where all the experimental activities happened. That's our expander rig, which is our power generation, and we have our internal heat recuperation. So in effect, any exhaust heat that is coming out of the system is actually being recovered within the system in the process. We mapped all of these things up and we created the digital twins of them to actually do all the exploratory studies that we want. This is just a parametric input-output that came out of some of our tests. The key number in bold here, just worth mentioning, is we are starting with something called an expander efficiency of our system at 50%, but when we start including all the losses into account, this thing really brings down back, and we are around at the 40% threshold. Now, keep one thing in mind, that this is a single-cylinder engine. Its efficiency are going to be slightly lower than when we are talking about multi-cylinder case. So what we want to really do with this overall project was to actually push that 40% as high as we can. This graphical layout just presents the different parameters that we can do and we can optimize in the split cycle engine. I'm not going to be showing any equations, but the best way to understand how a good optimized engine looks like, if you think about that red loop which is there, any area under that graph is how much effective your system actually is. The bigger that red loop is going to be, the more effective your system is going to be. So I'm just showing you that green loop along with the red loop. So that green triangle that is at the bottom, what that actually shows is it shows the advantages of having a cool compression and internal heat recuperation. So I'm kind of teasing you a little bit here with what the end result should look like, but the area under the graph is linked to efficiency. The greater area we can get, the more effective fuel to power conversion we can actually have. We want to do all of this, yet being fuel agnostic as far as the engine is concerned. So compression, waste heat recuperation, and expansion work is what we are going to be focusing on. So let's look at some of the compression results. So these are analytical results, so we kind of have a good appreciation of how much compression we actually need to opt in our compressor end of the cylinder. We want to opt isothermal compression. You can get more work savings out in the process. That is analytical, but we want to see what happened in the practical aspect. The most interesting bit that comes out of this practical graph, which is there, between 0.4 and 0.5, you see a small blip happening in that green and the brown lines. That is actually telling us from a practical point of view where the trade-off actually needs to be made. So around that 0.5 to 0.6 compression index number that we have, if we can maintain that, we can maintain practical systems in the process. There are other ways to optimize also the cooling part, but that's one of the route we have actually gone down. Now, the green dots that you're seeing on that line is actually mapping up the results, same what we're getting in the digital twins that we actually have. So Go back to that fact that I said, the more area under the graph that we are going to get, the more effective the system is going to be. Think about that red loop, which is a fully optimized diesel cycle, against the two other variants, the blue loop and the green loop, which is running at the split cycle mode in cool compression and internal heat recuperation, which straight away tells us we are getting a high efficiency in the overall system. So, heat recuperation. Every engine that is running out there, about 15% of all the energy of the fuel chemical energy is coming out in the exhaust tailpipe. We don't want to lose that. We want to internally recover all that heat. This is a heat recuperation setup, worked with one of the companies, High Flux Limited. The top graph up there shows the effectiveness of a heat exchanger there. We are getting up to almost 80% internal heat recuperation. And what you can see, one of the final numbers at the bottom right, which is written down there, we are able to actually recover 15% of the fuel chemical energy back into the overall system, which is actually just, if we were not to recover it, it will just go through the exhaust tailpipe. So that red line, straight red line, is where we started. And by doing cool compression and internal recuperation, we are able to make the area bigger and bigger, and we are able to get increased efficiency in the overall process. The variability, the fact that we have so many variables we can tune and optimize, allows us to make this type of engine architecture agnostic to the type of fuel. So the two different optimizations that have been run here, which were also shown in the experiments, they are being tailored for different fuels, because some fuels want more ignition energy to burn. They burn at higher temperatures, whereas others do not. So we are able to tailor the cool compression. We are able to tailor the internal heat recuperation. And as a result, we are able to tailor the demand of the top end temperature the setup actually requires. So let me just give you a little bit of overview of the power generation end of a setup. This is a single cylinder Titan engine where we are doing the power generation mode. The graphs on top and the bottom are showing the match and repeatability of what was happening in the experimental setup to what is happening in our digital twins. And we are able to pretty much match whatever the experimental setup is going to be doing within the plus minus 10% area. The final thing I just wanted to mention regarding the expansion optimization is, if you just look at the green line which is going on top, we are able to find a plateau beyond which we are actually not really getting any efficiency benefits. So we have now found a sweet spot of optimizing the combustion cylinder also without actually increasing any NOx in the process, because we are tracking the in-cylinder peak temperature. So this final graph is really what we were really after. We started with this kind of early 40% engine efficiency. By optimizing the cool compression, the internal heat recuperation, and expansion process, we are able to exceed that 55% efficiency threshold. Keep one thing in mind, this is a single cylinder engine. So 55% efficiency for a single cylinder engine is relatively high. So let me wrap this thing up with some take-home messages. So what I have done is I've kind of shown you the cool compression, the internal heat recuperation, and the expansion results coming from a split cycle engine architecture. The main thing that you need to get out of this thing is we must consider disruptive engine technologies that are going to be fuel agnostic and are going to be high efficiency if any form of transition roadmap needs to be implemented alongside any form of end goal use of a carbon-free fuel needs to be considered. I'm just going to wrap that thing up here. Thank you very much for your time.
Thank you, Angad.